Today we will discuss a small topic, carbocations. This term is very familiar to you because we have already studied this in both substitution reaction as well as elimination reaction. It is a major intermediate present in both substitution as well as elimination. Carbocations are a group of atoms having a carbon with only 6 electrons and a positive charge. So carbocations, they are group of atoms containing a carbon with 6 electrons and a positive charge. This is methyl carbocation. This is methyl carbocation. This is the central carbon or a carbon having 6 electrons. It is attached to 3 atoms and it bear a positive charge. Then next one, that is this is primary carbocation. Then next I will write an example of secondary carbocation. This is secondary carbocation, and this is example of tertiary carbocation. So all these carbocations, they have a carbon atom having 6 electrons and a positive charge. So such type of reacting species, they are known as carbocations. Like free radicals, these carbocations are also very reactive species because this carbon atom contains 6 electrons in its outermost shell and it requires 2 more electrons to complete its octet structure. So they are very reactive. As these carbocations receive a pair of electrons, they are also known as Lewis acids. So all carbocations, they are Lewis acid because they receive a pair of electrons. They are highly reactive because they lack a pair of electrons. Next we will move on to its structure of carbocations. Structure of carbocations. So the central carbon atom is attached to 3 other groups. Here I am showing it as hydrogen. 3 other groups and is aligned as a corners of equilateral triangle. All this central carbon atom as well as 3 other groups, they all are sp2 hybridized bonds. They all are sp2 hybridized bond. They all are aligned in a space or in same space, and the vacant p orbital that is, this is the vacant p orbital. This will be perpendicular to this plane. This central carbon atom and 3 other hydrogens, they are sp2 hybridized and they all are aligned in same plane. And this vacant p orbital, it is aligned perpendicular to this plane. So this vacant p orbital is responsible for its rearrangement, reaction and everything. This is the structure of a carbocation. Now we will move on to relative stabilities of carbocation. Okay. For this, we will discuss different heterolytic bond dissociation energy of different alkyl halides into carbocations. First, this is methyl bromide. It when dissociate, it will yield CH3 plus Br minus, and its heterolytic bond dissociation energy, that is delta H, is equal to 219 kilocalories per mole. Next one example is primary alkyl halide. that is ethyl bromide dissociates into CH3 CH2 plus Br minus. Its heterolytic bond dissociation energy that is equal to 184 kilocalories per mole. Next we will discuss, this is primary, this is methyl alkyl carbocation. Then next we will discuss secondary, that is CH3 CH3. This when dissociate we will get CH3 plus Br minus, and its delta H is equal to 164 kilocalories per mole. Last one, that is tertiary, this is secondary. Last one, that is tertiary, CH3 and here bromine. It will be dissociated into tertiary carbocation, and its heterolytic bond dissociation energy is equal to 149 kilocalories per mole. So comparing these different heterolytic bond dissociation energy, what do we mean by heterolytic bond dissociation energy? It is the energy required for an alkyl halide to dissociate into a carbocation and a halide ion. This energy is known as heterolytic bond dissociation energy. Here when we compare delta H of this methyl carbocation, primary, secondary and tertiary carbocations, we can see that the maximum energy requirement is for methyl carbocation, formation of methyl carbocation, and as we go down, that is primary alkyl halide or primary methyl carbocation, it requires only less energy than that of methyl carbocation, and the energy requirement decreases as we go from secondary to tertiary. So when we plot a graph of this, we will get, this is the delta H, we will get this is first one, that is CH3Br, that is methyl carbocation, it is formed into CH3 plus Br minus, that is 219 kilocalories per mole. Here we are using primary CH3 CH2 Br. Here it will be CH3 CH2 plus Br, and its energy requirement is 184 kilocalories per mole. Next one is secondary, this is methyl, this is primary. Next one is secondary, that is CH3 CHBr CH3. Here it dissociates into CH3 CH plus CH3 plus Br minus, and its delta H is 164 kilocalories per mole. And last one, that is tertiary, CH3 CH3 Br, and dissociate to gives tertiary carbocation plus Br, and its energy requirement is 149 kilocalories per mole. So energy requirement is in the decreasing order. So high energy requirement for methyl carbocation means that this methyl carbocation is least stable. And this less energy requirement for tertiary carbocation shows that this is highly stable. So the stability of carbocations is in the reverse order, that is stability order of carbocation is more for tertiary, then secondary, then primary, then methyl carbocation. So the stability of carbocation, least energy requirement is for tertiary. So it is more stable. The maximum energy is for methyl carbocation. So it is least stable. This is the order of stability. And there are some factors which affects the relative stability of these carbocations. First one is attacking group. So if this carbocation is attached to a group, that is electron releasing group is present, it will release its electron and it will nullify or disperse the charge of this carbocation, and this will stabilize carbocation. If another group G, it is electron withdrawing in nature, what will happen? It will withdraw electrons from this carbon and it will intensify the positive charge. The positive charge is intensified. Here it is reduced. Here the positive charge is intensified, and this will cause destabilization of this destabilize this carbocation, and the stability of carbocation is decreased. That is why this tertiary carbocation is more stable, because alkyl group, they are electron releasing groups. So this alkyl group will release electrons and the positive charge is nullified and it will stabilize as carbocation. But methyl group, it contains only hydrogen, it cannot nullify this positive charge, and so these carbocations are less stable. Electron withdrawing groups such as halogens, that will destabilize these carbocations, and this effect will be maximum when it is near to this carbon. If the distance between this carbon and the electron withdrawing group is increased, its effect is also decreased. Okay, then next important topic coming under carbocation is its rearrangement. Rearrangement of carbocation. So when we look into SN2 reactions and SN1 reactions and E1 reactions, which involves carbocation as a major intermediate, there we can see a rearrangement, or the product will be changed. Because this is because of the rearrangement of carbocation. We all know that tertiary carbocations is more stable than secondary and then primary. So always this carbocation shows a tendency to attain more stable form. That is, this primary carbocation, it always try to change into secondary carbocation. The secondary carbocation, it will always try to change or attain its stable structure as a tertiary carbocation. So this rearrangement of carbocation is another important factor. So there are two types of shift present in this rearrangement. First one is hydride shift, and second one is alkyl shift. So hydride shift, in this hydride shift, the rearrangement is done by the shifting or rearrangement of hydrogen atom, hydride atom, and the other one, this alkyl group is rearranged. So let me show you an example. Here CH3, CH2, CH2, H. This is the alkyl halide, and the carbocation is CH3, CH2, CH2 plus H minus. This is a primary carbocation. This will undergo a rearrangement. This will undergo a rearrangement by shifting this hydride ion to next carbon, and this positive charge is shifted to second carbon, that is CH3, CH, CH3. This carbon will have positive charge. What is happening here? This hydrogen, this CH2, one of this hydrogen will be shifted to the terminal carbon, and this positive charge is shifted to second carbon, and this has been changed to secondary carbocation. So secondary carbocation is more stable than primary carbocation. This is an example of hydride shift. Here the hydrogen is shifted to attain a more stable form. Next I will show you an example for alkyl shift. Here is the example. This dissociate into CH3, here CH3, here, and this is a second plus Br minus. So this is a secondary carbocation. What will happen here is this alkyl group, it will be shifted to this carbon, and this positive charge will be shifted to this carbon, and the rearranged product is CH3, CH3, CH3. This is a tertiary carbocation. This one is more stable than this secondary carbocation. So here this alkyl group is shifted to this carbon, and positive charge is shifted to this carbon, and we will get a tertiary carbocation which is more stable than that of secondary carbocation. This is the rearrangement of carbocation. Sometimes we will get a product that is entirely different from that of starting compound. This is the reason for that, that is these carbocations undergo rearrangement.